We talked about how to observe the position of an object, how to put a particle to represent the location of an object, and then how to lay out a coordinate axis, a coordinate system to describe mathematically the location of that object. The next thing we have to do is actually get numerical values. The numerical quantity representing the location of an object is its position. Again, if we're using a horizontal motion, horizontal in a straight line, we'll use x as our coordinate to represent position. If we were moving in a vertical direction, we might use y. Mathematically, these are all the same. What this variable x represents is the object's location relative to the origin at a given instant. Position is a vector quantity. The position vector points from the origin to the location of the particle, or it points from the origin to the location of another object. So as a vector quantity, we also mentioned before, a vector has two components to it. It has a magnitude and a direction. The magnitude here is the distance from the origin. This particle is 3 meters from the origin. This particle is 1 meter from the origin. The vector also has a direction. The sign, the plus or minus, tells us the which direction from the origin the object is. This is a +3 because we're 3 to the right of the origin. This is -3 because we're 1 to the left of the origin. Generally, position we're going to measure in meters in the SI system. The base unit in the imperial system is feet, and our conversion between the two is that 1 inch is 2.54 centimeters. So what we're going to do is look at the particles that we've measured. We're going to lay out our coordinate axis and define an arbitrary origin, and we're going to measure how far each particle is from our origin. That's going to give us a number, a numerical value that represents the position of the object, and we will have measured the time at which the particle was present at each location. So we're going to be able to read off of our motion diagram the position as a function of time, t comma x, and that's going to allow us to create a position graph. Again, t is our independent variable, t time is passing, and the position is the dependent variable. It goes on the vertical axis. The position depends on what point of time we have. And so we can look at each particle's position. We can graph the position at a point in time. And by looking at the shape of this graph, we can interpolate, we can sort of connect the dots, and that shows us how the object is going to move. Once we have the position graph, we can start doing our calculus-based analysis to understand where the particle is, how fast is it going, is it speeding up or slowing down. All of the mathematical operations we can start to do once we have a function to describe it rather than a picture. So the picture is a good place to start to take our observations. We turn that into a graph or a function, and once we have the graph or the function, we can start doing analysis. One example of the analysis that we might do is to find the average position of an object. You might have an object that is moving back and forth, and so the object is always in motion, it's always at different positions, but you might say the average position is right in the middle, because half the time it's to the right, half the time it's to the left, and so that would be our average position of the object. The way that we find that is by using what's called the average value theorem. You saw the average value theorem in Calc 1. What that does is it says that the area under the actual position function, x of t, should be the same area as the average value. The average position should be a constant value. That's what an average means. And a constant value in a graph is a horizontal line. So the area under this horizontal line is a rectangle. It's the length times the width. The area under the arbitrary position graph is the integral of those. We divide both sides by t, by the width of the interval, and we end up with this equation here. Another way of thinking of the average position is that if you want to find the average value of a set of numbers, you would add up all of the numbers. You would add up x1 and x2 and x3 and divide by the total number of quantities that you're adding up, and that would give you your average value in sort of the standard sense. If you have a graph, you don't have a few distinct, discrete values to add up. You have a continuous function. You have a continuous different, infinite number of positions at different instances in time. And so you're essentially doing the same thing. You're adding up the position here and the position there and the position there and the position there and the position there and the position there. And as you add all those up, you see what we're doing is to add up all of these positions. It means finding this area, which is the integral part. Adding all of them up. How many are we adding? We're adding up however much time we have in our interval. So this is dividing by the number of terms that we're adding up to find the average value. So to find the average value of any quantity, you integrate that function over whatever interval you want, divide by the width of the interval, gives you the average value of that function, of that value on that interval. This is the average value theorem from Calc 1, and we're going to see this over and over again for many different quantities.